I'm very glad to share my recent work, joint work with Alexeyev and Yan on the WKB analysis of certain meromorphic linear system. Yeah, it's a pity that I cannot go back to Swiss and give this talk in person. Now, please allow me to share my screen with you. Right.
Yeah, so we
okay.
see the, yeah, perfect.
Great. So today, as I said, I can talk about some WKB approximation of a very particular system of meromorphic ODEs. But of course, this conference is about Vertex algebra and Poisson geometry. So I gonna mainly say some insights. On this question from Poisson geometry, as we're gonna see, hopefully. Okay, great. So I'm not going to, give a detailed introduction to what are the WKB analysis for the Schrödinger equation or some second order differential equation. What I can say here is that, so this is basically a method to find the asymptotic solutions of Schrödinger equation in a perturbative way. So this was developed around 1986 for finding the asymptotic solution. And later on, around the 1980s, Worrells incorporate the Borel resummation method to this formal, WKB method to introduce a so-called exact WKB analysis. So roughly speaking, this is a method to solve second order, to solve Schrödinger type equation by starting from, a formal solution, formal expansion in H bar, and then do the Borel resummation in some local chart, and then try to globalize your solution by finding the connection formula between, different local solutions. I don't have enough time to cover this. If you know it, you know it. But in this talk, I'm gonna talk about some, WKB analysis for some higher order differential equation. Just give some quick comment on the exact WKB analysis for higher order differential equations. What are the states? Higher means the order of your equation is higher than or equal to 3 equation. Somehow this theory, as far as I can say, is not quite well established. There are two main difficulties. So one is that, as in the Schrödinger equation case, we can always find a formal, formal H bar expansion solution. But the thing is that we don't know if the formal solution is summable or not. So that is, we cannot easily resum the formal solution. So this is one difficulty. And another one is that in the exact WKB analysis, you should resum your formal solution in some sectors, and you cannot resum it in a uniform way. Therefore, there exists some Stokes phenomena inside. So therefore, you will encounter some difficulties to decide what are the so-called Stokes graphs. Like, even though you know the Borel summabilities for the formal solution in any local region, you don't know. I mean, it's difficult to extend the local solution to some global region. So there is some difficulty from the combinatorics, like the complexity of the Stokes graphs in this higher order Poisson case, right? But today, I'm gonna talk about the goal of my talk is somehow to study some global aspect of the WKB approximation of some prototype linear system of ODEs. With a pole with some irregular singularities, as we're gonna show later on. And the method in my talk is sort of using the Poisson geometry. Using the Poisson geometry. The Poisson geometry on what? On the space of the monodromy data. Of your system. Yeah. So sorry, now I can hear my voice. So okay.
Sorry, it may be my fault. Sorry.
No, it's fine. Right? Okay, great. So the Poisson geometry on the space of the monodromy data, and also the tropicalization of the Poisson structure, as I'm gonna explain later on. Yeah. So this is my goal and the strategy for today. Okay, very good. So the system for today is simply a meromorphic linear system taking this form. So I consider this linear system where this coefficient is given by some data of U and A. Here is F is some, so this is a meromorphic system over some Z plane. And F is a invertible n by matrix valued function. And I assume U is a diagonal matrix with distinct real components. I'm gonna use this regular carton of real to denote the set of diagonal matrices with real eigenvalues, distinct real eigenvalues. And this A is an arbitrary Hermitian matrix. N by N Hermitian matrix. It's a constant. And I take the square root of -1 for some reason. Yeah. And of course, you can also view this as a nth order ODEs. But I prefer to think of this as a system. Okay. And this here I put this parameter epsilon, which is a non-zero real number, which is a very small number. You can think of it as a Planck constant in WKB of Schrödinger equation. Right. So I said I'm gonna study the global aspect. So the global aspect is that I care about the monodromy data of this system. Let me introduce what are the monodromy of this system, some global data for these ODEs. So that are the so-called Stokes matrices. So roughly speaking, if you take any solution of any meromorphic solution of your system, you can try to compute the asymptotics of Fz as Z goes to 0 from different directions, in particular from right or left half plane. Then you will figure out actually there exists constant matrix such that this is some quite general fact I'm gonna recall a little bit. So you will figure out Fz has the following asymptotics behavior in the near 0. So Z times bracket A. So this bracket A takes a diagonal part of matrix A times Fz is asymptotic to certain invertible constant matrix T plus or minus as Z goes to 0 in left or right half planes. I use IH to denote the half planes. IH plus means the right one, minus means the left half plane. So roughly speaking, Fz around this irregular singularity, Fz has an exponential type of behavior, and from different directions. So its asymptotics are different, controlled by some invertible matrices. Then we can compare the difference of these asymptotics to measure this jump of this function Fz near this essential pole. So we can measure this difference of asymptotics by introducing this Stokes matrix. Sorry, here I'm gonna use S U A epsilon to simply denote, as I said, the ratio of these two invertible matrix. So this is simply an invertible n-by-n matrix. So one can think of it measure the different asymptotics of the solution Fz. So here there exists some epsilon here, right? Yeah. So if this is the first time you see the Stokes matrix, I give you an example, like the 2x2 case. Let's see what exactly it describes. So in 2x2 case, the Stokes matrix here actually measure the connection formula for Kummer function. So in 2x2 case, our system taking this form, you have some U1, U2, two real values, plus 2 pi I, and the residual matrix is Hermitian. So you have some real diagonals and A conjugate complex of A times F. One can rewrite this as a second order equation, like in Schrödinger equation type. And then one can write down the solution directly by using the Kummer function. Eventually, by the known asymptotics of Kummer function or confluent hypergeometric function, one can easily find that the Stokes matrix in this case takes the following form. It's given by the diagonal element is exponential T1 over epsilon and the exponential T2 over epsilon. And the element in the first row, second column looks complicated, but it's still explicitly given. Let me write down it. T1 minus T2 over epsilon. And you have more terms. So divided by gamma of 1 minus lambda 1 minus T1 over epsilon times T2 over epsilon. Yeah, so this is how the Stokes matrix looks like in 2x2 case. So here, lambda 1 and lambda 2 are simply the eigenvalues of the Hermitian matrix A, which are two real numbers. So as I said, in this case, the Stokes matrix is nothing but the connection formula of Kummer function. So I can give a simple remark. What are the Stokes phenomenon? You can, if this is your first time to see it. So if we go to the Wikipedia, it says that the Stokes phenomenon, which is exactly this jump of the asymptotics of the solution Fz in different directions. The Stokes phenomenon states that a function, for example, on the complex plane, can have different asymptotics in different zone or different directions as z approaches to some critical point of the function Fz. Yeah. And in 2x2 case, the Stokes matrix exactly counts the Stokes phenomenon of Kummer function, defined as a sort of twist of the exponential function. I guess most of you know this expression. This is the Kummer function is given by this form Paul series expression where an is a standard notation which denotes the product of a plus 1, and so on up to a plus n minus 1. Right. So we can easily see this function has an essential pole around infinity, and it has polynomial type growth as z goes to infinity from the left, and have some exponential type of behavior as z go to infinity from the right. So this function has a Stokes phenomenon. Yeah, which is exactly how we compute the Stokes matrix in 2x2 case. Right. So as I said, this Stokes matrix, we have seen it in Philip and Valerio's talk, I guess. So they are actually what I mean by global data. So if you know WKB for quadratic differential, this is sort of the exact the summation of the Warrow symbols of our system. Okay. And in the following, my goal is to study the asymptotics, to try to understand the asymptotics of this global monodromy, which is simply the invertible Stokes matrix as epsilon go to 0, to try to understand the leading asymptotics of this guy. So in 2x2 case, if we look at the explicit formula and using the expansion formula for gamma function, we can see that the leading asymptotics take this exponential type. And the only thing interesting is in the first row, second column, and it's given by exponential of maximal value between lambda 1 and lambda 2 over epsilon. Here again, recall that lambda 1, lambda 2 are the eigenvalues of Hermitian matrix, the 2x2 Hermitian matrix, which are real numbers. The asymptotics of the Stokes matrix in 2x2 case simply take this form. Okay, so this is a sort of introduction to the problem. Any questions? Okay, if no question, let's see. So in the following, I'm gonna use some combinatorics data or some algebraic data on some spectral curve to understand this asymptotics. So to explain why this is possible, let's give you some fake analysis to try to understand what's this question. Okay, so because I'm gonna use this equation from time to time, let me write it one more time. So I put all this 2 pi I, so for just for the convention to be simple. Okay. So the fake analysis says that first, we can try to find the epsilon expansion solution. So we can try to solve this equation in a perturbative way. That is, we can write the equation, some formal equation in the power series of epsilon. And we can assume the solution somehow taking this following form, plus some higher order terms of epsilon k. So as epsilon go to 0. So this is a formal power series. And of course, we are talking about the fundamental solution. That is anything here are diagonal, are n by n matrix. And VZ is also n by n matrix. I denote each of its column by VK and Vn. So this is an n by n matrix. I only write down its column. Then simply by comparing, by looking at the leading asymptotics, this is quite easy. So if you look at the leading behavior with respect to epsilon, we will easily find omega z and Vz, these two matrices, should satisfy the following equation. So the derivative of omega with respect to k as a number times this column should equals to the coefficient of our system acting on the column vector. Okay, so in other words, the derivatives should be the eigenvalues, and in the meanwhile, the column vector should be eigenvalues for the associated eigenequations, right? So if here we think of the eigenequations, or actually the equation which determine the spectral curve is given by this guy. So we can see that if we write the power series solution, the leading terms should be related to this algebraic curve defined by these eigenequations. Okay, now let's see what this fake analysis tells us. The fake analysis tells us that to study the asymptotics of Stokes matrix is exactly it tells us the Stokes phenomenon. Takes place in the asymptotics, or in other words, the WKB approximation of the Stokes matrix as epsilon go to 0 should be encoded, right, by some algebraic data on the curve defined by the eigenequation. This is simply, if we recall what's the definition of Stokes matrix, we see exactly the leading asymptotics of Stokes matrix should be encoded by some jump of the or some period on this spectral curve if we go through this analysis. Okay, but of course this is a quite fake analysis. So in the following, I try to give more sense to what I said in this page. Now, first, let's give a quite precise conjecture which summarized what I said. So how to understand this WKB approximation of global asymptotics. So the first thing is that I should introduce some coordinates on the space of Stokes matrix. on the space of upper triangular matrix. So this is simply, this takes a minor of a J by J matrix formed by intersecting the columns I minus J plus 1. So if I have a n by n matrix like the Stokes matrix, I take the first J rows and I take the column between I minus 1, I minus J plus 1 and I, or I must, I must say something wrong. So this should be probably J minus I. Right? Yeah. And I take the minor of this guy. So in the end, I take more or less n squared over 2 minus, which can be seen as a coordinate on some open chart of the upper triangular matrix. So in the meanwhile, I introduce a spectral curve. Spectral curve. This is denoted by UA. So this curve is assigned to a pair of data UA, and it has genus. If we compute carefully, we will find out its genus is more or less n squared over 2. So determined by exactly the eigenequations. So this is a curve in the Z and the lambda plane. And to be more precise, you should complexify in P1 times P1. So this is in lambda and Z plane. Okay. And now the conjecture proposed by Anton me and Yan Zhou is the following. So this is a precise version of the fake analysis. So we conjecture that actually for generic U and A, if I have time, I'm gonna explain what are the generic means. So for example, you want your spectral curve to be smooth, right? So then there exists a canonical, or actually a set of cycles. Let's call it CKI. So here again, this CKI certify the K and the indices I and K certify this condition. So that are certain cycles on your spectral curve such that the period, such that the pairing between cycles and the canonical one form on your spectral curve is exactly the WKB leading term of your Stokes matrix. So that is, if we take the minor coordinates of the Stokes matrix assigned to U and A, then we take this limit. So we see that the expression, this limit expression exactly takes exponential leading term. Yeah, I guess you know what I mean. So this must coincide with the period on your spectral curve. So this is a canonical one form, or some people call it Seb-Witten, I guess. Right. So this is our conjecture, which more or less this is basically what I meant in the previous page for the fake analysis. So the leading asymptotics of Stokes matrix should be encoded by some periods on the spectral curve. So before, as I said, I'm gonna give some Poisson geometric insights why this is true and how to deal with this problem. Although it's still a conjecture, but before that, let me see. Let me give some quick remarks. So for example, in 2x2 case, you can verify it by hand. right? Because the Stokes matrix has a quite explicit formula, and the spectral curve is actually a P1 to P1, two cover from P1 to P1, so it's also computable. But in general, to understand the left-hand side, you will encounter some analytic difficulty. So this is the left-hand side. I'm not sure people understand this very well now. And in the meanwhile, so this is actually more or less corresponding to the summability in the exact WKB business. And in the meanwhile, on the right-hand side, you also have some difficulty. The difficulty comes from the determination. So how to choose the right cycles if they exist. So this is more related to the Stokes graph, or it's also called a spectral network. Network in the physics context by Giotto, Moore, and Netsky. Right. So the main difficulty to understand this problem is what I, as far as I can say, there are two major difficulties. Okay. Now I'm gonna try to explain this, or try to give some strategy to understand this question from Poisson geometry. So recall that if we look at this conjecture, this is sort of non-trivial, right? Because the left-hand side is sort of discrete data. What I mean is that the cycles somehow lives inside the integer coefficient of your curve. If you want the periods, if you want the pairing between the canonical one form to match up with the asymptotics of Stokes matrix, so this is not so trivial. So our strategy is as follows. So let's first, everything here, like the Stokes matrix or the spectral curve or the differential equation, are parameterized by U and A. Here, I have to say again, U is a diagonal matrix with real entries, and A is a Hermitian matrix. And let me write down the configuration space of U and A. And what we conjecture is that generically this should be true. That means that there may be some lower dimensional stratum where the conjecture is not true, either because the WKB, either because the limit on the left doesn't exist, or the curve, or the curve on this low stratum is non-smooth, like in the discriminant locus of the polynomials. So there may be some lower dimensional stratum. But somehow the strategy we use is that first, we're gonna study using some analytic method using some asymptotic solution to Riemann-Hilbert problem to try to determine or choose these canonical cycles in certain horizontal or in certain zonal region of U and A. So in this configuration space, H regular, the real points of regular Cartan times Hermitian matrix by Hermitian matrix. So we're gonna, for example, we're gonna first decide for any point, U and A living inside this zonal region, how to choose the cycles on the right-hand side of our identity, and then how to understand this inequality or try to prove it near this point. And on the other side, we try to use some Poisson geometry method. Actually, the first analytic method is also sort of Poisson geometric. I'm gonna comment later. The Poisson geometric method to find some guiding principle. You know, to extend the cycles. If our conjecture is true, we want to find some guiding principles to extend the cycles from this small zonal region to all of the space of U and A. Yeah. Okay. So this is our strategy. So now, in the following, I'm gonna first tell you how to choose and how to prove this conjecture in some special point you cut. So in the following, so recall that we want to compare some analysis data that is a limit of the Stokes matrix. Right. And then, so this is defined by U and A, and then try to compare it with some period on a spectral curve defined by the same U and A. So our strategy is we compute separately these two data near some special point. That is a U-cut. So let me first introduce what are the U-cut. So U-cut is, so the right way to understand U-cut is to simplify, to take the discontinuous process compactification of H regular. But here, let's simply say it's a asymptotic zone. So let's simply denote U-cat is a asymptotic zone of U, certain asymptotic zone. So this is simply any diagonal elements are real. So the asymptotic zone is basically we let UK or UK plus 1 goes to 0. So for each k minus 1, I can also denote it by U1 much less than U2, although this may be misleading, but by this, what I mean is exactly UK or UK plus 1 goes to 0. So this is some asymptotic zone in U in the space of U. And then we prove in this asymptotic zone, the conjecture is true. So again, with Anton and Yanzhou, we show that actually we compute this data and show that, so we compute the analysis data. So many brackets, so let me see. Okay, so we compute this guy and prove that this is actually given by the sum of the eigenvalues of sub-principal matrix of the Hermitian matrix A. So here, as I said, lambda K1, so lambda KK are the ordered eigenvalues of the case principal, like the left top K by K submatrix of the Hermitian matrix A. Yeah. Right. So first we compute this thing. So, you may ask why, So in general, as I said, the Stokes matrix more or less reflect some connection formula for some transcendental function. Like in 2x2 case, its computation is equivalent to the connection formula for Kummer functions. For higher order, for higher rank case, in general, people have no idea how this looks like. So how we compute these things? This is simply because it's based on my previous work on the asymptotic solutions. I don't have enough time to explain this, but let me just tell you why we can compute this limit. So actually, we compute some Riemann-Hilbert or maybe Bokov Riemann-Hilbert problem asymptotic solution. That is actually we solve this Riemann-Hilbert problem or find the explicit formula for the Stokes matrix as U, in the asymptotic zone. And the expression is given by taking this form. I'm not sure if it's a good idea to write down the formula. Let me just write one term of this formula. If you know the representation of, if you know the Gelfand-Zeilinger theory, you will recognize this is closely related to the Gelfand-Zeilinger theory. So the K, so here I'm computing the K0 and K+1 count. Each of these entries has explicit formula, but let me just give you some subdiagonal entries of Stokes matrix. So it's given by some formula taking this form. So each of this box is also the product of gamma functions. And recall that these lambdas are the eigenvalues of sub-principal matrix of A. And just as 2x2 case, if you know this asymptotic solutions to Riemann-Hilbert problem, you can easily compute the leading asymptotics using the asymptotics of gamma functions, which gives you the theorem above. So more or less here in this step, so to solve this, to understand this conjecture near this zonal, region, we have to use some analysis, to use some asymptotic solutions to Riemann-Hilbert problem. This is what I mean by analysis here. Okay. Right. Now we have computed the left-hand side. Let me compute the right-hand side. So how to compute the periods? So this can be seen as step 1. So we want to compare in this asymptotic zone, we want to compare the analysis data and the periods. So how to compute the periods? It's also sort of hard to compute the periods on algebraic curves. To compute curves near this or at this asymptotic zone, that is as U1 much less than U2 and so on. So how to compute the periods? Right. So this computation turns out not so hard. So the pattern is that if we fixing U1 and UN minus 1 and let UN goes to infinity, we will see that, as I said, this spectral curve has genus n minus 1 times n minus 2 over 2. And if you look at the shape of this curve, you will find out as one of the components go to infinity, there will be n minus 1 cycles, separate out from the rest. And so let's call it C1, C2, C3, and so on. So there are n minus 1 of them. So So as UN goes to infinity, there is a canonical way to separate out so n-1 cycles. So actually, as UN go to infinity, they becomes vanishing cycle, which means that in this limit, the curve actually degenerates to the following. So each of these C1s become vanishing cycle. So I'm not sure if I can draw it very well. So the left has n-2 times n-3 over 2 genus. The right is simply a disk with punctures now. Right. So this is like a puncture disk, and each of these C1, C2, and Cn becomes vanishing cycles. Right. So this is some observation, and in the meanwhile, it's sort of easy to compute the periods over this vanishing cycle. And before that, let me also say, so we can iterate this step, right? We can then let U2 go to infinity and so on. Eventually, what we get is sort of unpunctured disk attached to each other. And on this degenerate curve, we have in the end more or less n squared over 2 canonical cycle, which is coming from the vanishing cycles. And let's label them by CKI. And it's also not hard to compute, vanishing cycle. We'd better call them VKI. And it's also easy to compute the periods of this VKI for the canonical one form pairing with this vanishing cycle. This is given by the ith eigenvalue of the case submatrix of A. So this is a lemma. Okay. So in this page, I explained in this asymptotic zone what the spectral curve looks like and how their periods are computed explicitly. Now we simply comparing these periods, explicit periods, and this explicit asymptotics, we sort of get the conjecture is true in this asymptotic zone. So this is not quite precise, but I only have 10 minutes left, so I haven't explained where the Poisson geometry comes from. So let's just formulate like this. So just a simple summary. So on the left-hand side, we use some asymptotic solution to Riemann-Hilbert problem to compute the asymptotics of Stokes matrix. And then on the right-hand side, we use this degeneration of spectral curve. And from there, we can canonically choose the vanish cycle and compute their periods. By comparing these two computations, by a direct computation, we show the conjecture near some asymptotic zone. Okay. Now, as I said, so we only propose the way to understand the conjecture in some asymptotic zone. Now the thing is that how to understand the conjecture in a global way. So like how to, if you remember the graph I draw, right? I have tell you near this caterpillar point how to choose for each generic point how to choose cycles, right? Another thing is that we want to extend the cycles. If, for example, at this point UA, we want to choose some cycles, right? And show that the periods of the cycles coincide with the asymptotics of Stokes matrix. Well, if you may think that if there is a path inside this open dense part, you can, along this path, all the spectral curve are smooth. Then you can just by continuity, you can get the cycles, right? Because the cycles are in Z coefficient. But somehow it may happen, we didn't check, but it may happen you should close some wall, right? And even you may have some weird monodromy. Therefore, there may be some non-trivial piecewise linear transformation on H1, Z coefficient H1. So how to understand this behavior? So this is, so how to control, how to understand this behavior. This is sort of the spectral network thing, if you know what they are. So let me give some insights from Poisson geometry. Okay, now, so recall that it was found by Philippe Bolt. First, he generalized the Atiyah-Bolt construction from flat connection to meromorphic one. In particular, he introduced Poisson structures on the space of Stokes matrices. Furthermore, he proved that the Riemann-Hilbert Birkhoff map is actually a Poisson, locally Poisson diffeomorphism, which is a Poisson diffeomorphism restricted to the real slice. So that is the following Riemann-Hilbert map for any fixed U. So Riemann-Hilbert map, which taking the Stokes matrix of the ODE determined by UA. So this is where the A lives, and to the space of. So this is simply the set of upper triangular matrices with real diagonals. Sorry, I should denote this with arrows, not with maps. Okay, so this map assign any A simply to the Stokes matrix of A. For each non-zero epsilon, he proves that this is actually a Poisson diffeomorphism. So this is a particular example of the linearization of the Ginsburg-Weinstein linearization thing. Okay, so this theorem gives a lot of constraints on what the Stokes matrix should look like, right? For example, well, if you know the Poisson bracket on the right, the Poisson bracket on the left is of course the KK of the canonical linear Poisson, while on the right are some certain Poisson structure given by some classical RLL formulation. And this map is a Poisson. There are many consequences. For example, immediately you can recognize any of the elements of Stokes matrix is determined in a quite explicit way by the subdiagonal ones. This is simply from the Poisson bracket, Poisson structures on Boson side. And now we try to get more out of this. And then we try to incorporate the epsilon limit with the Poisson structure. So now, because what we was study in this talk is actually the epsilon goes to zero limit. So now we need to understand what is Philippe's theorem, right? Theorem as epsilon goes to zero. So this was answered in several papers of Anton Arkady Yanpeng and Benjamin Hoffman, Jeremy Lin. So let me recall. So as I said, what am I gonna say due to right, I try to recall. Yeah, so they have a series of joint works. So I'm not sure I can say which one is which one. Let me just write all of their names: Hoffman, Lin, Jeremy Lin, and Yanpeng Li. any of, yeah, I guess in this talk I'm gonna use, right? Right. So their theorem can be simply summarized as follows. So as I said, we want to understand, what's the analog of Borch theorem as epsilon go to 0. We should first understand what are the analog of the dual Poisson-Lie group as epsilon go to 0 and so on. So in the end, it's summarized as follows. If any diffeomorphism from UN star, which is isomorphic to the space of n by n Hermitian matrices with a canonical linear Poisson structure, but rescaled by epsilon. If you have any Poisson structures, Poisson diffeomorphism, so this is a family of Poisson diffeomorphism. Then they studied the epsilon limit. Furthermore, if you have a family of epsilon family of Poisson diffeomorphism such that the following limit exists. So this is exactly the leading asymptotics of your diffeomorphism, right? So we can basically insert this diffeomorphism to be the Stokes given by the to be the Riemann-Hilbert maps exists for example, generic A. Then they show that if this limit exists, then they subtract from this existence the following important inequalities. So that is, if they exist, then for each A, the limit should satisfy the Rhombus inequalities for all the K and I's. Okay, very good. Well, this is another constraint, right? We can get from Poisson geometry on the study of Stokes matrices, because we simply combine Philip and Andon Arkady and their collaborators' result as a corollary. We see that if our mini conjecture is true, right, then the periods must satisfy this Rhombus inequalities. Okay, so if I can have one more minute, I gonna give one more comment. So this is a very strong constraint if you think of it, right? Because what we want to do is we want to compare the analysis data with some algebraic data. And the thing is that we first determined how the cycles looks like in some region, and we want to extend. And the thing is that as we extend the cycles, there is some guiding principle, which is we propose, which is inequalities. And there is one last comment I have to add, is that this inequalities is actually, I don't have enough time, but this is actually the same thing as, so this inequality encodes the same data with Bernstein-Kachtan potential of the unimportant radical of a Borel subgroup. Let's just say the space or on the space of Stokes matrix, or the space. It's not quite that, but yeah, space matrices. Right, let's mention this. This inequalities encode the same Yeah, sorry that I guess my time is up. So there are some more remarks, but I may not. Let me just end at this point. I hope I explain this strategy completely. Thank you.
Let's thank Xiaomeng for the interesting talk. Maybe first from the online audience.
Can I ask a question? So, hi, Xiaomeng. So, is it possible to do analytic continuation in this UA space to avoid those walls and consider complex matrices A and U?
Yes, this is a very good question. So actually, only yeah. Let me give you answer. So actually. So there is an important stuff here I didn't mention. I only consider the real slice, right? This is because the real slice is what appears in representation theory. If we study the if we want to compare the Stokes matrix with some shift of argument subalgebras, so in the quantum case. And but it's more, of course, it's more natural, right, to study algebraic geometry to be in a complex setting. So the thing is that in a complex setting, we can imagine. So we have UA, and we have some low-dimensional stratum where the Stokes matrices, where the conjecture is not true, but it's generically codimension 1 in complex dimension, right? Therefore, there are some monodromy. So there are some monodromy. So this means that, of course, the monodromy on the periods is sort of variation of Hodge structure. So the variation on the Hodge is a variation of the H1 of the spectral curve. For your question, I would like to say a very important thing on the limit of Stokes matrix. So how do you see, the asymptotics of, let's simply say Stokes matrix, ignore the delta ij. So what are the monodromy on the left-hand side? This monodromy comes from purely analysis. So recall that even in 2x2 case, or in general case, asymptotically, this Stokes matrix looks like gamma functions of some difference of eigenvalues and so on. Right. So there are some similar terms. Now, if we go to the complex setting, and we multiply this number of some 2 pi exponential I theta, and we let theta goes around from 0 to infinity to 2 pi, from 0 to 2 pi. Now, simply from the asymptotics of gamma function, we know that the gamma function is not, the asymptotics of gamma function is not uniform. It has no well-behaved asymptotics along the negative real axis. Therefore, on the complex setting, the Stokes matrix, the leading asymptotics of Stokes matrix will have some jump. And this jump, I guess this jump is, so we see that this jump simply from analysis, like from the asymptotics of gamma function, which is not uniform. So this jump from analysis should match with a variation of Hodge structure. And similarly, it should match with the jump formula, or the so-called DDP jump formula, or it's called the BPS. In the Guyot-Moore-Netsky, it's called, there are some. I mean, this is a quadratic. Yeah. Anyway, so so let me not comment on this. Anyway, I hope this answer your question. So if we go to the complex setting, as you said, we may avoid the real codimension one thing, but the thing is that we may have monodromy. A new problem arises, but it's much more interesting because the monodromy may count for the cluster mutation. Because I haven't mentioned cluster structure, but the minor coordinates I took in this talk is actually a clustered seat on the unipotent on the Borel subgroup. And I guess this monodromy from either analysis or from this variation of Holt structure may be related to the cluster mutation, as may be predicted from spectral network and so on. Yeah, or in Gontarov and his collaborators talk from using in complex setting some new phenomena.
Thank you.
Thank you.
Any more online questions? If not, are there any questions from the local audience? Actually, I have a basic one. So do you expect that to work for other compact groups because all the ingredients seem to be available?
Right.
So the system is also generalized to those groups.
Right. Of course. So of course we can ask for any compact group, or we can ask more, right? We can ask for higher order case. So I'm not sure if in Philip's talk he talk about this model space of meromorphic connection with arbitrary poles. There are notion of superpotentials and so on. But the thing is that in my talk, one important thing is that, so this is other types. So we need at least understand the analysis in some region. So we need the asymptotic solution to Riemann-Hilbert to the Stokes data. Otherwise, we have no way to compare two sides. And I didn't talk about, basically we solve this conjecture only in this asymptotic zone. And I tell you, if the conjecture is true, how to extend using some algebraic method, how to possibly extend to other region. There is also analysis way to attend the asymptotics of Stokes matrix using the isomonodromy method. Isomonodromy and isospectral correspondence. But this is also very hard. We haven't worked out how to extend the analysis data from the asymptotic zone to the generic region. But all of this first depends on the asymptotic solution to the Riemann-Hilbert problem. We have to first compare some initial data. For other types, this is sort of hard because some new transcendental function arises, and but of course we still believe this conjecture should be true. But the thing is that there is some analytical issue for other types. For your question, but of course the Poisson geometric side is already done in your work with Anton and so on. So the Poisson geometric side, like Boltz's result, extends for arbitrary reductive groups, even for higher order case. And Arkady and Anton and the collaborators' work also works for arbitrary types. But the thing is that the analysis side is not worked out yet.
Well, let's hope it will. So let's take
Thank you. Thanks again.